On July 16, 2026, somewhere inside a control room at NASA's Jet Propulsion Laboratory in Pasadena, a small team of engineers is preparing to send a set of instructions across 25 billion kilometers of empty space to a machine that has been flying since before most of them were born, and nobody in that room can promise it will survive the attempt. The spacecraft is Voyager 1. The command is nicknamed the Big Bang, and somewhere between the moment it leaves Earth and the moment, nearly 2 full days later, that a reply either arrives or does not, an entire 50-year story of exploration will hang on a single roll of the dice. This is not a metaphor invented for drama. This is the literal situation facing the most distant human-made object ever built. A machine so far away that light itself, the fastest thing in the universe, needs 23.5 hours just to reach it. Voyager 1 is dying, slowly, deliberately, by design, but dying nonetheless. It has been dying for years, in fact, losing about 4 watts of electrical power annually as the plutonium-238 inside its radioisotope thermoelectric generator decays according to a clock that no human intervention can stop. And now, after nearly 49 years of outrunning that clock, the Voyager team has decided the only way to keep buying time is to gamble everything on one enormous, irreversible maneuver, executed all at once on a spacecraft they cannot see, cannot touch, and cannot fix if it goes wrong. To understand why this command is so dangerous, you first have to understand what has already gone wrong, because Voyager 1 is a machine with scars. In October of 2024, the spacecraft's fault protection system triggered unexpectedly after engineers turned on one of its heaters in the probe's X-band radio transmitter. Its primary voice to Earth shut itself down. For a moment, mission controllers thought they had lost their spacecraft. Days later, the fault protection system triggered again, and Voyager 1 switched to its S-band transmitter, a backup system so old it had not been used to communicate with the probe since 1981, back when Ronald Reagan was newly in the White House and the spacecraft was still threading its way past Saturn's rings. Engineers scrambled, listened, recalibrated, and eventually coaxed the primary transmitter back online by mid-November. The spacecraft survived. But the incident revealed something the team already suspected and now had to confront directly. Voyager 1 was no longer just old. It was fragile in ways that could not always be predicted, running systems that had never been designed to operate for half a century, in a place colder and lonelier than any engineer on the original Voyager team could have fully imagined when they built it in the 1970s. The Big Bang maneuver is the next chapter in that same fight for survival, and it is, by NASA's own description, a genuinely high-stakes undertaking. The idea itself sounds almost mundane when you first hear it described. Swap out a group of powered devices all at once, turning some things off and switching in lower power alternatives to keep the spacecraft's electronics warm enough to keep functioning. That is it. That is the plan. But the danger is not in the concept. The danger is in the execution. Because on a spacecraft flying through the near absolute zero void of interstellar space, warmth is survival. And a mistake in how power gets redistributed during that swap could mean losing the delicate thermal balance that keeps Voyager 1's remaining instruments, and its ability to point its antenna at Earth from freezing solid. If the fuel lines that control its thrusters were to freeze, the spacecraft would lose its lock on Earth entirely, and the conversation, already stretched to the edge of patience by distance, would go silent forever. There would be no way to send another command, no way to diagnose the failure, no way to recover. Voyager 1 would simply keep flying, deaf and mute, carrying its golden record into a darkness with no one left to answer. This maneuver has already been tested once, cautiously, and not on the spacecraft you might expect. Engineers chose Voyager 1's twin, Voyager 2, to go first, precisely because Voyager 2 has slightly more power to spare and sits somewhat closer to Earth, making it, in relative terms, the safer subject for a first attempt. Those tests ran through May and June of 2026, watched by a team that understood every second of data coming back was a preview of what might be waiting for Voyager 1 itself. Only if Voyager 2 came through cleanly would the team dare attempt the same swap on its older, more depleted, more distant sibling. And that is precisely where the story now stands in the exact week you are hearing this, as engineers prepare to send that same high-stakes command outward to Voyager 1. A full generation older than the spacecraft that just tested it, carrying less power and sitting more than 2 billion kilometers farther from home. Nobody on the team is calling this routine. Kareem Badaruddin, the Voyager mission manager at JPL, has been candid about the balancing act his team faces daily, describing the goal simply as keeping both Voyagers going for as long as possible, even when that means sacrificing pieces of the mission to save the whole of it. Because sacrifice is the pattern here. And it did not begin with the Big Bang. In April of 2026, engineers made the difficult decision to permanently shut down Voyager 1's low-energy charged particles instrument, known as LECP. an instrument that had been running almost continuously since launch in 1977, measuring the ions, electrons, and cosmic rays drifting through both our solar system and the wider galaxy beyond it. That shutdown came after a routine roll maneuver in late February caused an unexpected and alarming drop in the spacecraft's power levels, one that brought Voyager 1 dangerously close to triggering its automatic undervoltage fault protection, a self-preserving shutdown sequence that, once activated, would have forced a slow, uncertain multi-day recovery. Rather than risk that cascade, the team chose to retire LECP themselves on their own terms, buying Voyager 1 roughly one more year of breathing room. That single year is the entire window in which the Big Bang must now succeed. There's no second chance waiting in reserve. If this command fails, there's no backup plan sitting on a shelf, because for a spacecraft this old, this far away, and this fragile, every remaining option has already been used at least once before. What happens in the coming days will either extend a 50-year story of survival against every reasonable expectation, or it will mark the moment humanity's furthest reaching machine finally goes quiet, mid-sentence, 25 billion kilometers from anyone who could ever go and check. To feel the true weight of that risk, you need the numbers, because the numbers are what turn a dramatic story into an engineering reality. Voyager 1 sits, as of this week, more than 25.4 billion kilometers from Earth, or roughly 15.8 billion miles, a distance so extreme that it will not even be the spacecraft's final milestone this year. On November 18th, 2026, at 2:16:07 in the morning, Pacific time, Voyager 1 is projected to cross the threshold of a full light day from Earth, a distance of 16,094,796 miles, the moment it becomes the first human-made object in history that light itself needs an entire day to traverse. Right now, in mid-July, a radio command leaving JPL's antennas takes approximately 23 hours to arrive at the spacecraft. The shutdown sequence for an instrument like LECP, once received, takes about 3 hours and 15 minutes to fully execute. Add it together, and engineers commanding. Voyager 1 today are working on a nearly 2-day communication loop for every single exchange, sending an instruction and then waiting and waiting and waiting before they even know whether the spacecraft understood them correctly, let alone whether it responded the way they hoped. The power problem sits underneath all of it, and it is a problem rooted in physics that no amount of clever engineering can ultimately reverse. Both Voyager probes carry a radioisotope thermoelectric generator, a device that converts the heat released by the natural radioactive decay of plutonium-238 into usable electricity. At launch in 1977, each spacecraft produced approximately 470 watts of power, enough to run a full suite of 10 scientific instruments alongside heaters, transmitters, and the gyroscopes needed to keep antennas locked on a planet shrinking into the distance behind them. Plutonium-238 decays with a half-life of about 87 years, which sounds forgiving until you realize the decay is only part of the loss. The thermocouples that convert that heat into electricity also degrade over time, and the combined effect has been a steady drain of roughly 4 watts every single year, year after year, for nearly 5 decades. Of the original 10 instruments each spacecraft carried, only 2 remain active on Voyager 1 today: the magnetometer, which measures the magnetic fields of the interstellar medium, and the plasma wave subsystem, which listens to the charged, ionized gas that fills the space between stars. 7 other systems have already been sacrificed, one at a time, in a shutdown sequence that scientists and engineers actually mapped out years in advance, ranking every instrument by scientific value and power draw so that when the moment came to make a cut, the decision would already be made calmly, rather than in a panic. This is what makes the Big Bang maneuver so fundamentally different from every previous power-saving step. Turning off an instrument is subtraction, a known, controlled, and reversible in theory action that engineers have practiced for years. The Big Bang is substitution performed simultaneously across multiple systems, swapping older power-hungry components for lower power alternatives all at once, a single coordinated action, rather than a slow sequence of individual cuts. The reason for combining it into one event, rather than spacing it out safely over months, comes down to the thermal architecture of the spacecraft itself. Powered components generate heat as a byproduct, and on Voyager 1, that waste heat is not incidental. It is essential, keeping critical electronics and, most importantly, the hydrazine fuel lines that feed the spacecraft's thrusters from dropping below their freezing point in an environment where the ambient temperature sits barely above absolute zero. Cut power gradually and unevenly, and you risk creating cold spots in the wrong places at the wrong moments. Swap the entire configuration at once, calculated carefully in advance, and you have a chance of landing the spacecraft in a new stable equilibrium, warm enough to survive, efficient enough to keep transmitting for potentially years longer than the current trajectory would allow. Consider the scale of what a successful swap might buy. NASA's own estimates suggest the shutdown of LECP alone bought Voyager 1 roughly 1 year of additional operating time. If the Big Bang succeeds, where that single shutdown could not go further alone, engineers believe there is a genuine possibility of freeing up enough reserve power to switch the LECP instrument back on, something that would have sounded like science fiction only months ago. AGO. That is why, when the team deactivated LECP in April, they deliberately left one small component alive within it, a half-watt motor that rotates the instrument's sensor to scan in every direction. It draws almost nothing, but keeping it spinning preserves the mechanical possibility of a resurrection. Bet that the Big Bang might just work well enough to bring a retired piece of 50-year-old hardware back from the dead, out past the edge of the solar wind, where no repair truck, no astronaut, and no backup part will ever be able to reach it. Behind every watt of power being fought over today stands a story of people. Because Voyager 1 was never just a machine, it was a decision made by human beings who understood they might not live to see how it ended. The mission traces its roots to a rare planetary alignment, occurring only once every 176 years, that would allow a single spacecraft to use gravity assist to visit Jupiter, Saturn, Uranus, and Neptune in one continuous grand tour. NASA originally conceived the probe as Mariner 11 under the Mariner program, before budget cuts scaled the ambition back to a flyby of Jupiter and Saturn alone, and the spacecraft was renamed Voyager, as its design diverged enough from its Mariner heritage to earn its own identity. It was built at the Jet Propulsion Laboratory, launched on September 5, 1977, 16 days after its twin Voyager 2 left the pad, and given a decagonal, 10-sided bus, 16 hydrazine thrusters, and 3-axis stabilization gyroscopes designed to keep its antenna locked on a home planet that would only ever grow smaller. In its rearview mirror, the engineers who built it were told the mission would likely last 4 years. Nobody involved was planning for 2026. And yet, here they are, an entirely new generation of engineers, most of whom were not yet born when Voyager 1 slipped past Saturn's rings, now responsible for keeping a 50-year-old machine alive, using documentation, instinct, and a communication link measured in whole days rather than seconds. Kareem Badruddin has spoken candidly about the emotional weight of decisions like the LECP shutdown, describing it plainly as something nobody prefers to do, but that remains the best option available, a sentence that captures the entire philosophy of the modern Voyager team. Preserve what you can, sacrifice what you must, and never pretend the losses do not matter. Elsewhere in the mission's extended family sits Matt Hill, principal investigator for the LECP instrument at the Johns Hopkins Applied Physics Laboratory, who wrote after the April shutdown that the instrument had allowed scientists to discover the properties and effects of cosmic rays and solar particles, and to sense the very changes in the surrounding region that told humanity, for the first time, the precise moment Voyager had crossed out of the solar system and into interstellar space. His words carried a quiet grief and a quiet hope in the same breath, expressing that the team holds out hope the engineers' new plan might power the instrument back up, so they can continue learning whatever surprises still wait for Voyager in these distant, unmapped regions. This is not the first time the Voyager team has had to reach into the past to save the present. In December of 2017, engineers fired all 4 of Voyager 1's trajectory correction maneuver thrusters for the first time in 37 years, since they had last been used in 1980, gambling that dormant hardware built during the forward. Administration would still respond to a command sent across interstellar space. It worked, and the maneuver extended the spacecraft's ability to keep its antenna pointed at Earth by an additional 2 to 3 years, buying time nobody had budgeted for. Then, in October of 2024, an unexpected fault protection trigger knocked out the primary X-band transmitter entirely, forcing Voyager 1 onto its long-dormant S-band system, a backup that had not carried the spacecraft's voice since 1981. For a stretch of days, the team effectively had to relearn how to listen to their own spacecraft using equipment from a different technological era, before finally restoring the primary transmitter and resuming full data collection by mid-November. Layer these events together, the 2017 thruster gamble, the 2024 transmitter fault, the 2025 shutdown of Voyager 2's own LECP instrument as part of the same conservation strategy, and a pattern emerges that defines the entire modern Voyager program. Survival here has never come from a single brilliant fix, but from a long chain of smaller, riskier decisions, each one buying just enough time for the next. There is also, threaded quietly through all of this, the matter of what Voyager 1 still carries with it, physically, into the dark. Bolted to its side is the Golden Record, a gold-plated copper disc engraved with sounds and images meant to represent life and culture on Earth. A message addressed to nobody in particular and everybody at once, intended to outlast the mission, the team, and possibly the species that built it. Every command the Voyager engineers send today, including the one now heading toward the spacecraft. is in some sense also a decision about how much longer that message keeps traveling with a working escort, still capable of confirming, however faintly, that someone back home is still listening for a reply. If the Big Bang succeeds, it will not simply extend a single spacecraft's lifespan, it will rewrite the assumptions engineers hold about what aging hardware can survive, decades after the people who designed it ever imagined it operating. NASA's own internal projections, cited across the agency's recent communications, suggest that with power, carefully managed, both Voyager probes could continue operating into the early 2030s, a horizon that would have sounded absurd even 10 years ago. Reaching that horizon would mean Voyager 1 crossing its 50th launch anniversary in September of 2027, still transmitting, still listening, still the only human-made instrument capable of directly sampling the plasma and magnetic fields of true interstellar space from that exact vantage point. No other spacecraft, not Voyager 2, not New Horizons, not any mission currently funded or even proposed, occupies remotely the same position. Voyager 1 is not simply far away, it is uniquely far away, and every additional month of operation is data that literally cannot be collected any other way, by any other machine, for any price. That uniqueness is precisely what raises the stakes of every decision the team makes now. The interstellar medium. Voyager. While one is sampling, the thin, ionized plasma left behind by the deaths of nearby stars millions of years ago behaves differently than the solar wind that dominates the environment inside our solar bubble. And scientists are still working to understand exactly how the two interact at the boundary Voyager 1 has already crossed. The plasma wave subsystem and magnetometer, the two instruments still functioning, continue to detect pressure fronts, density changes, and magnetic fluctuations in a region of space where our models remain incomplete, built largely on assumptions rather than direct measurement, because until Voyager 1, nobody had ever measured it directly at all. Every additional year of data from this specific machine, at this specific and ever-increasing distance, refines those models in ways no simulation or telescope observation can replicate. Because telescopes see light from enormous distances away, while Voyager 1 is physically present, its instruments literally bathed in the particles it studies. There's a broader engineering legacy at stake as well, one that extends well past the Voyager program itself. Every technique the current team develops to squeeze additional years out of a decaying power source, every workaround for aging hardware operating far beyond its design life, every method for diagnosing a fault across a communication delay measured in days rather than milliseconds, becomes a body of institutional knowledge that will directly inform future deep space missions. Spacecraft like New Horizons, already well past Pluto and continuing into the Kuiper Belt, and any future probe intended for the outer solar system or beyond, will eventually confront the exact same problem Voyager 1 faces now. A radioisotope power source in inevitable decline, and a team on Earth forced to choose which capabilities survive and which get sacrificed first. The Big Bang, whether it succeeds or fails, on Voyager 1 becomes a permanent entry in that shared engineering record. A real-world test case for exactly how far power management, thermal balancing, and calculated risk-taking can extend the working life of a machine nobody can ever physically visit again. Consider, too, what this means for the science of the heliopause itself. The boundary Voyager 1 crossed back in 2012 when it first left the protective bubble of the sun's solar wind and entered true interstellar space. That crossing was itself identified, in part, using data from the very LECP instrument now sitting dormant, waiting to see whether the Big Bang can bring it back online. Scientists still debate the precise shapes and behavior of the heliopause, whether it flexes and breathes with the sun's roughly 11-year activity cycle, whether it develops the kind of pressure fronts and turbulent structures Voyager 1 has already detected passing through, and how sharply or gradually the transition from solar to interstellar plasma actually occurs. A revived LECP would let researchers resume gathering direct measurements of that boundary's ongoing behavior, years after the initial crossing, offering a second and third look at a phenomenon no other instrument in history has ever observed firsthand. Losing that instrument permanently would not erase the earlier data, but it would close the book on any future refinement, freezing our understanding of this particular transition at whatever level of detail the mission managed to capture before the power finally ran out. And should the maneuver fail, the lesson will be just as valuable in its own harder way. A failed Big Bang would not simply end one mission, it would establish, for the first time under direct observation, the actual failure threshold for a 50-year-old radioisotope-powered spacecraft attempting a coordinated multi-system power reconfiguration at extreme distance and extreme cold. That is, knowledge engineers currently do not have, because no spacecraft has ever survived long enough or traveled far enough to test it. Whatever happens to Voyager 1 in the coming days becomes, either way, a data point that did not exist before, purchased at the cost of the very spacecraft that generated it, sent outward by people who will not know the outcome for nearly 2 full days, and who built their entire careers around a machine most of them will never actually see reach its end. So where does this leave us, in mid-July of 2026, waiting on a signal that has not yet arrived? The honest answer is that nobody knows, and that uncertainty is not a failure of planning, it is the fundamental condition of operating a machine this old, this far, and this alone. Even if the Big Bang succeeds precisely as intended, the reprieve it buys is measured in years, not decades, because plutonium-238 does not negotiate, and the thermocouples converting its heat into electricity will keep degrading, regardless of how cleverly engineers rearrange the remaining watts. Somewhere in the early 2030s, by NASA's own estimates, both Voyager spacecraft will very likely fall silent for good, not through any single dramatic failure, but through the same slow arithmetic that has governed this entire mission since the moment of launch. Continuing their journey outward as drifting relics, carrying the golden record towards stars, they will approach only after tens of thousands of years, long after everyone currently working the mission, and everyone currently watching it, has been gone from this world for a very long time. But the questions this moment raises reach beyond Voyager 1's own fading power budget. Somewhere out past the reach of its transmitters, the true edge of the sun's gravitational influence, the outer boundary of the Oort cloud, still lies tens of thousands of astronomical units farther than Voyager 1 will ever travel. A reminder that even humanity's most distant machine has barely stepped past our own solar system's front porch. What does interstellar space actually look like farther out, in regions no spacecraft, current or planned, will reach for centuries? What happens? To the plasma wave measurements, once Voyager 1's remaining instruments finally do go dark, and no other craft is positioned to pick up where it left off, NASA has floated concepts for future interstellar probes, potentially propelled by nuclear or advanced solar sail technology, designed explicitly to travel faster and farther than the Voyagers ever could, but none currently exist beyond early design studies, and none will launch before Voyager 1 itself falls permanently silent. For the foreseeable future, whatever the Big Bang does or does not achieve in the coming days will represent the absolute limit of direct human sensing at true interstellar distance, a limit that will stand unchallenged for years or possibly decades after Voyager 1 stops answering. Meanwhile, the missions that could eventually carry humanity's curiosity past the point where Voyager 1 leaves off remain, for now, largely conceptual. Proposals for an interstellar probe, studied by teams including the Johns Hopkins Applied Physics Laboratory, envision a spacecraft capable of reaching several times Voyager 1's current distance within a human lifetime, carrying instruments far more sensitive than anything available in 1977. But such a mission remains unfunded and unlaunched, which means that for a gap of years and possibly decades, there may be no active instrument anywhere in true interstellar space at all, nothing waiting to pick up the exact moment Voyager 1 goes quiet. That gap is part of what makes every additional month the Big Bang might purchase so disproportionately valuable. There is something almost unbearably human buried inside that fact. A species that dreamed of reaching the stars sent 2 small machines outward in 1977 with a 4-year mission plan, and instead built almost by accident the longest-running conversation in the history of spaceflight, one that is now stretched across nearly 50 years, 3 generations of engineers, and a distance so vast that the very act of saying hello and waiting for a reply now takes the better part of 2 full days. Every command sent to Voyager 1, including the one now crossing that void, as you listen to this, is really a small act of faith, an assumption that a 50-year-old machine built with 1970s technology still remembers how to listen, still knows how to answer, and still wants, in whatever sense a machine can want anything, to keep going a little further into the dark. Whether the Big Bang succeeds or fails will be known within the next few days, quietly, in a status update, on a NASA webpage rather than a headline event, but the answer to that quiet update will determine whether one of the boldest experiments in human history gets to keep speaking, or whether the most distant voice humanity ever sent outward finally, after 49 years, runs out of things to say.